to Poland, did his PhD from there. Some very high level of good works as I was talking to him in quantum information theory, possibly from the Mecca of information theory in the world, I would say, because you people are young. Just check out the work of this Oroloki family in quantum information theory, and so now he's back here in SNBOS as a national postdoctoral fellowship, and soon hopefully we'll get into somewhere guiding more students like you. But Debashis is fairly approachable. You have a very good understanding of the principles of quantum mechanics, foundations, and applications. Now you see introduction to self-testing of quantum devices. Debashis, state of yours.
Yeah, thank you so much, sir, for this nice introduction. So I would like to thank the organizer for organizing such a splendid summer school in this difficult time, and it's a pleasure to be a part of it. So today I'm going to talk about self-testing of quantum devices. So it would be a very introductory talk. So first I will motivate why we need self-testing, and then I will describe what is self-testing, and then I will talk about why self-testing is important. And since it is a summer school, I would give you proof for the simplest self-testing statement for quantum devices. I will give you the mathematical proof. Okay, so let us first start with the postulates of quantum theory. So if we have an operational approach, then we would like to describe devices rather than the physical systems. So this is a preparation device, and X is the parameter that you can control. So X is a classical variable, and for different values of X, it prepares a different quantum system. Right? And the quantum theory says that if it is a pure state, then we can represent it by a unit vector that belongs to some Hilbert space, or if it is a mixed state, then it is represented by a density matrix that belongs to the operator acting on the Hilbert space. Okay. So then we have a measurement device, and if it is let us consider the ideal measurements. That is the projective measurements. So it receives a quantum system and performs a measurement on it and returns a classical outcome. So here A is the outcome and Y corresponds to different measurement settings. So for different values of Y, it performs different measurements on the system, and it gives you the outcome which is labeled as A. Okay, so it is described by a set of, so if it has D different outcomes, then we can represent this measurement by a set of D projectors. So Y corresponds to the measurement settings and A corresponds to the outcome. So this is a set of this is a set of projectors such that it should satisfy this condition. Okay. And so we can perform. So we can prepare a state corresponds to the variable X, and we can, let's say, performs measurement on the system corresponds to the variable Y, and we can make this experiment many times, and then we can get the statistics or the probability. That is, what is the probability of getting outcome A if I choose the parameter X and Y for the preparations of the measurements, and this is given by the Bond rule by this formula, and for the density matrix it is given by this formula. And if we get an outcome A, then the state would collapse to another state, which is given by this, which is the collapse postulates of quantum theory. So this is the measurement device, and then we have a transformation device, and in the ideal case it would be represented by a unitary matrix, and it basically receives a system, and after the transformation, we will get a state which would be connected by some unitary operator by this formula. Okay, so let us ask the question that suppose a quantum device is given to a user, and the question is how can be the user sure that the quantum device truly functions in a non-classical way as specified by the provider. And this is not just a simulation of classical systems. So this is the question that we'll address. So we need some methods to certify that these are indeed quantum systems. So suppose a preparation device is given to me, and it is said that it creates some entangled states. And a measurement device is given to me, and it is said that it performs certain measurements on it. So how can we verify that? So the brute force method is we break the device and see all the internal functioning of the device. So how it works and everything. We go through all the details of the device, and we can be sure that okay, it works in this way. But this is very complicated, and this is not operational at all. So another method, which is normally known as the tomography of quantum system. So using tomography, we can know unknown state of an unknown physical system, and we can know unknown measurement by tomography. But for the tomography, we need at least some knowledge about the device or the physical systems, and also it is required to trust other devices which will be used for this tomography. So, for example, let's say this preparation device prepares a qubit which is in an unknown state given by this. So to know the unknown state, we have to perform a tomographically complete measurements, a set of tomographically complete measurements, and that could be sigma x, sigma y, and sigma z, for example. And if you do some small calculation, you will see that the probability of getting outcome 1 given if we measure sigma x, which is a function of nx. So if you measure sigma x, sigma y, and sigma z, and from the observed probabilities, you can you'll be able to know the vector nx, ny, and z. Okay, and thus you can you'll be able to know the state. But for this, we need to know the dimension of the system, and accordingly, we have to perform a set of tomographically complete measurements on it. And we have to trust this measurement completely. So we have to know that, okay, these are exactly the measurements sigma x, sigma y, and sigma z. Otherwise, we will not be able to know the state. So in other words, so we get the statistics at the end of the day. If we do not assume anything about the internal functioning of the devices, at the end of the day, we will get these 3 statistics. So this measurement device performs 3 measurements and gives certain statistics. And these statistics can be easily simulated by a classical system. So for example, suppose this preparation device doesn't prepare anything, let's say, and this device has 3 random bit string. So such that so the 3 string corresponds to, let's say, the variable x, y, and z, such that the probability of 0 is 1 by nx by 2, and the probability of 0 in the next string is ny by 2, and something like this. And each time you perform a measurement, it basically gives the output from the string. So if you press x, then it gives the output plus if it is 0, and if it provides the output -1 if it is 1 in the string. So you see that these statistics can be easily generated by classical system. So the problem that we address is, suppose we have these probabilities. We don't know anything about the devices. We have only the observed probabilities, and then can we infer about the quantum states? Can we certify the quantum states only from the statistics or not? Okay. So this is the question that we will address. And to do that, so we need to know we need to use some quantum correlation that cannot be simulated by classical system to ensure that indeed this comes from the quantum devices. And one of the best, probably the best way to certify quantum correlation is to do a Bell test. So I think there is one talk already on the Bell's inequality. So I will briefly go through about Bell test. So the experiment is as follows. So there is one preparation device, and in each run of the experiment, this preparation device prepares a system which has two subsystems, and one subsystem goes to Alice and another subsystem goes to Bob. And Alice and Bob, they have a measurement device each, and they can perform, they can choose the measurement settings by the variable X and the Y for Alice and Bob respectively. And after they perform the measurements, they obtain the outcome, let's say A and B. So basically in each run of the experiment, a preparation is prepared by the device, and Alice and Bob measure the subsystem randomly that depends on the variable X and Y, and obtains the outcome A and B. Now, the measurement event on Alice's side and the measurement event on the Bob side, they are spatially separated. Okay, so that no information can travel from Alice to Bob and vice versa. Okay, so this is the requirement. And after many rounds of this experiment, they can communicate, and they will obtain the joint probability from this experiment. Okay, so they will choose X and Y in different values in different rounds, and at the end of the experiment, they will be able to know the observed probabilities. So let us take the simplest example. So suppose X and Y, they can take two values. So there are two measurements that can be performed by these two devices. Okay, and those measurement settings are denoted by 1 and 2, and each measurement yields two outcomes, +1 and -1. So if they choose X is equal to 1 and Y is equal to 1, then there are four probabilities. What is the probability of getting outcome +1 and +1, and +1 -1, and -1 +1, and -1 -1. So for each settings, they will observe four probabilities, and there are four settings. So four possible settings. It could be 1 1, 1 2, 2 1, and 2 2. So there are 16 probabilities they will observe from this experiment. Okay, so now let us assume something about the underlying physical system that is supposed to reproduce those statistics or the observed probabilities. So let us assume that the individual system is described by the physical state lambda, and so lambda has the information about the measurement outcome, and it is such that the measurement outcome of Alice's side depends on lambda and Y, but it is independent on Bob's measurement choice and Bob's outcome, and also Bob's outcome B is independent of Alice's measurement choice and outcome. So this lambda acts as a common cause of the outcome of these two measurements. So there is no direct cause because these two measurements are spatially separated, are performed on spatially separated labs. So that's why it can be explained only by the common cause. And we also assume the freedom of choice, that is the measurement, the choice of measurement settings is independent of the state lambda. Okay, so and so now for this, if we assume this, then the joint probability that they observe should be reproduced by this formula, and this is this is known as the joint probability that can be produced by the local theories. So you can so this new lambda could be arbitrary distribution over the lambda. So in each run, the lambda could be different, and there could be arbitrary distribution of the physical state. But for each lambda, these two probabilities should be independent. And in quantum theory, if the preparation device prepares a state psi, and as I told you before, that these measurements represented by a set of projectors, and this measurement also represented by a set of projectors, and y and x is the measurement settings, and a and b corresponds to the outcome. So the probability should be obtained by this formula. And basically, Bayes' theorem tells us that there exist some probabilities that cannot be reproduced by the local theories. So that is what Bayes' theorem essentially says. So it basically means that if you ensure that these two measurements are spatially separated, then there exists some statistics, or there exist some observable probabilities that cannot be explained by any, that cannot be reproduced by any classical system. So that is the main take-home message for our purpose. So let us come back to this simplest scenario where Alice and Bob has two measurement settings, and the outcomes are binary for each measurement. And this quantity, which is a function of those 16 probabilities, which is defined as follows. So this is the correlation between Alice and Bob, given that the measurement settings is 1 and 1. So x is 1 and y is 1. This is defined by this formula. So if the outcomes are same, then there's a positive plus sign. And if the outcomes are different, then there is a minus sign. So indeed, this is a linear function of those 16 joint observed probabilities. And one can show that this quantity should be less than 2 for any local theories or any classical theory. And so there exist 2 qubit state, which is the 2 qubit maximal state. And if you choose the measurement settings to be sigma z and sigma x on Alice's side, and the measurement settings on Bob's to be like this, to be in this direction. So this is the xy plane on the block sphere, let's say. And the measurements are chosen as follows. And then you can find that the value of this quantity would be 2 root 2, which is greater than 2, of course. Well, so it basically gives you a certification of quantumness, that there are, so if we have a violation of this inequality, that we can certify that indeed this quantum, this preparation device and these measurements has some quantum properties. Now we would like to know about the state and the measurement from the statistics, from the 16 probabilities. So let us see that if we have a state, if let's say the preparation device prepares the state psi, and if the measurement devices measures the observable corresponds to, let's say, this AXA and BYB, then the probabilities is given by this. Okay. Now, from the probabilities, can we say about what can we say about the state and the measurement? This is the question. So let us first notice that let's say if this is the set of states and the measurements that reproduces observed joint probabilities, then if we apply local unitaries, arbitrary local unitaries on Alice and Bob's side, then the new set of states and the measurements will be denoted by this. And this set will give us the same observed probabilities. Okay, so it is very easy to check. So at least we cannot distinguish between this state and this state. So this local the local unitary we cannot detect from the observed statistics. And also, if this set of states and measurements gives us set of joint probabilities, then it could be like the state with some auxiliary system, so it's an ancillary system, and the measurement is like it is performed on the state side, but the trivial measurement is performed on the auxiliary system on both sides. So this will also give us the same joint probability. So we cannot distinguish whether there exists an auxiliary system or not. And if we also include both of them, then also it is not very difficult to see that this is the new set of state and the measurements. So let us calculate. If we calculate the probabilities, which is given by this state and measurements, which would be denoted by P tilde, and it is basically given by it should be a sandwich of this state with these observables, and this unitary and this unitary will cancel out on analysis side, and this unitary and this unitary will cancel out on the both side. So it would be like this. And since there is a trivial measurement acting on the auxiliary system, we can write it as a product, and this is of course 1. So it would give us the same statistics what the state psi and this observable would give. So basically, we cannot distinguish these 2 degrees of freedom from the observed statistics. That we are sure about. Now, can we specify a unique state and a unique set of measurements from the statistics up to this freedom? So this is what self-testing does. So it actually infers a unique state and a unique set of measurements up to this 2 degrees of freedom. So so on one hand, we have shown that at these 2 degrees of freedom we cannot distinguish from the observed probabilities. Then the self-testing gives us a unique state and the unique set of measurement up to that degrees of freedom. So just to give you an example, so if the value of this CHSH inequality is 2√2, so let's say it is coming from arbitrary state a psi and the arbitrary set of measurements A1, A2, B1, B2. So these are binary outcome measurements. So these we can take as the Hermitian matrix. Okay. So it says that any state and the set of measurements gives us the value 2√2. There must exist 2 local unitaries, UA and UB, such that if we apply this local unitary on this unknown state psi, it should be a maximally entangled state of 2 qubit with some auxiliary state. And also that local unitaries would give us the measurements will be like sigma z times identity on the auxiliary system and sigma x times identity on the auxiliary system. And on the Bob side as well, this would be these 2 measurements which was told earlier. So, this is the exact statement of self-testing. So it's like this preparation device prepares certain system, and this measurement device performs certain measurements. So you get the statistics, and if the value of the joint probabilities is such that the value of beta is 2√2, then we are completely sure that basically this preparation device prepares the 2-qubit entangled states, and this measurement devices measures this particular set of measurements up to sub local unitary. Okay, and so this is like a blind tomography. You do not know anything about the internal working of the devices, but only from the statistics you can infer the states and the measurements. So, but in the experiment, in the actual experiment, we will not observe the maximum value 2√2. We will observe something less. So this is the robust version of the self-testing statement, which is if there is an unknown state psi and a set of measurements A1, A2, B1, B2 that gives us the value 2√2 minus epsilon, or the epsilon is some small positive value. Then there exists a unitary on analysis side and pop side, such that the distance between the ideal scenario with the 2-qubit maximally entangled state and this particular measurements and the unknown state should be bounded by some function of epsilon. So this is a measure of distance between two states. This is the Hilbert-Smith norm, and if these two are the same, then it should be 0, and if these are far apart, then it would be larger and larger. So it basically gives you a robust statement that if I observe something less violation of the Bell inequality, then the state and the measurements in these devices are also close to the state which are the 2-qubit entangled state and this qubit measurements. So just one remark is that for an exact self-testing statement, if you want to infer a unique state and a unique set of measurements, like I specify, then the optimal violation of the Bell inequality is necessary. But this is not sufficient. So there exists Bell inequality, but their optimal violation does not specify the states and the measurements. But in this case, it is. But this is necessary. I mean, if you want to specify a state and the set of measurements, the optimal violation is a necessary condition. Okay, so I will just briefly talk about what is device-independent information processing. So it is like the devices has the classical inputs and outputs, and the user doesn't know anything about the internal working of the devices, and the manufacturer of these devices is eavesdropper herself. So this is the most, let's say, the difficult scenario one could think of to perform some information processing protocol. So just to give you an example, suppose somebody says that, okay, this preparation device prepares the quantum state in the quantum state of a qubit in the up direction of the sigma z measurements, and it performs sigma x. So the probability of outcome +1 and -1 is half. But so can we use as a random number generator can you use this as a random number generator? So the answer is no, because we need to trust that indeed this device prepares this particular state, and this device measures this particular measurements. So from the statistics, we cannot ensure what is the quantum state and what is the quantum measurements inside the device. So it could be like this, that there is a string of random bits, and it just gives the output from that random bit. So to perform some device independent information processing protocol, we need to certify the quantum systems only from the statistics. And as you see, that self-testing gives you the maximum information from the statistics. It gives you a unique state and the unique set of measurements that is possible to give, which is possible to give from the observed statistics. So this is the most complete form of device independent certification. And one of the two most important applications of self-testings are the quantum random number generator and the quantum QKD, like quantum key distribution. So as I said, like any classical random number generator would not give you a genuine randomness because the classical theory is deterministic. And secondly, you need to trust the device. While the quantum device can give you a genuine random number, and it would be a device independent in the sense that you don't have to trust what is inside the device. So classically, it is impossible to execute device independent protocols, because classically you have to trust, either you have to trust the device or you have to open the device and verify it yourself that it works according to the promise of the provider. And as you probably know that the secure communication that we have nowadays is the security there is mostly based on the computational complexity. So for example, if I give you a huge number and ask you the prime factorization of the number, then any classical computer would take a huge amount of time. So the security is based on this fact, but there are quantum algorithms that can that are more sufficient to know the prime factors. For example, source algorithm. So yeah, so once we have a full-fledged quantum computer, the many of the classical security that we have will be broken. And on the other hand, quantum gives us device-independent quantum security. So you don't have to trust the device, and still you can communicate securely. And there, the security is based on the laws of nature, so it doesn't rely on anything. So that means that if we have a quantum device, like device-independent quantum key distribution device, then we are sure that at any time in future, there will be no possibility such that the security will be broken. So it is a permanent, it gives us a permanent solution in terms of the security. So well, so I think that's all I wanted to say in the first section. So if you have any, so I will now try to give you a mathematical proof of the self-testing statement. But if you have any questions so far, please ask me.
Anybody wants to ask a question, you can unmute yourself and ask.
If no, then I will go to the derivation of so this self-testing is not just physically interesting, and it has lots of application. The mathematics behind it is also quite beautiful. So this is the CHSH inequality that we have, and I have multiplied by factor 1/√2, such that the local bound is √2 and the quantum bound is 2. So so these are binary outcome observable, and without loss of generality, we can take these observables to be projective measurements. Because any, if you know about the generalized measurement, those are termed as a POVM, and any POVM can be realized by a projective measurement on high dimensional Hilbert space. And since we don't assume anything on the on the dimension of the Hilbert space, So we can safely assume that these measurements are projective. So this is the projector corresponds to the plus outcome, and this is the projector corresponds to the minus outcome. So the self-testing statement is the following. So if I have a state and a set of measurements they're acting on arbitrary Hilbert space. So we don't know the dimension of the Hilbert space. This could be arbitrarily large. But if the statistics from the state and the measurements maximally violate this Bell inequality, then there exists a unitary UA and UB such that we have the 2-qubit entangled state with some auxiliary state, and the measurements are the ideal measurements with some trivial measurement acting on this auxiliary system. Okay, so there are actually 3 methods to derive the self-testing statement in the literature. So this is actually very, let's say, this topic is quite recent. So, you cannot find this proof in probably in any paper, but this proof essentially is from one of our paper, but that is done for a more like generalized Bell inequality, not for the CHSH. But if you consider CHSH inequality, then the proofs will boil down to this one that I will show, and it only involves linear algebra. But apart from that, you can use other 2 techniques. Those are the providing a quantum channel or the semi-definite programming. These 2 methods also are shown to be useful to prove self-testing statement. Well, so just to tell you that if you are familiar with the Jordan's lemma, then the proof would be more easier than this one. But I would like to give you a proof that is self-contained. So I'm not going to use anything. So so just to tell that this proof can be made easier. Okay, so as I said that without loss of generality, we can assume that these are projective measurements, and for the since these are binary outcome, so these are also satisfy these 2. So the square of the measurement of Hermitian operator should be identity. Well, so this is the Bell operator where A1, A2, B1, B2 are arbitrary observables that are acting on arbitrary dimension we don't know. And the maximum value of the Bell inequality in quantum theory would be this. So the value of the Bell operator, and we will take the inner product with the psi, and we choose the best possible state and the best possible measurements. So this is the maximum value of the Bell inequality. Now, so this beta is an operator, and it acts on some arbitrary dimension Hilbert space. So this acts on some HA tensor HB, and you know that for any operator M, this is a positive operator. So the eigenvalues of this operator is always non-negative. It's very easy to check because for all state, this is greater than or equal to 0. So let us consider this operator. So eta is a real number, and identity is the identity matrix that are acting on this Hilbert space, and beta is my Bell operator. So if I can write down this operator in terms of sum of positive matrices, then what happens is if we take inner product with the state psi on both sides of this equation, then I know that this will give us a positive value always, because for each I this is a positive matrix, and on the left hand side this would give me the value of the Bell operator, and this is eta. So, and on the right hand side is always greater than 0. So eta is the upper bound of, so this holds for any size. So eta is the upper bound of this Bell inequality. So if you can write like this. So let us remind that the operator is like this. And if we define two operators, C1 and C2, by the linear combination of B1 and B2, then it is easy to see that this operator, you can take common out A1 from here and A2 from here, and this would be written as like this. And let us choose M operators like this and M2 operator like this. So identity minus A1 tensor C1 and identity minus A2 tensor C2. And let us try to calculate this expression. So this is a positive, this is a sum of two positive matrices. And if you do that, and then if you replace C1 to be B1 root 2 and B1 minus root 2. If you do the algebra, then you will see that this value will cancel out and you have to use the fact that a x square and by square should be identity, and then you will see that 2 into identity. So as a sum of positive operators, so 2 is the upper bound of this Bell operator. And I know that there exists a state and the when that it gives us the maximum value, then so on the left hand side it should be 0, and this should be 0 as well. And since each of them is a positive operator, follow this equation, which means that mxi should be 0 for all x. So and mx is chosen like this. Okay, identity minus a1 tensor c1 and a1 tensor a2 tensor c2. So this should hold, and this basically means that we have this set of two equations. So we so basically we have to solve these equations and say that and we have to prove that okay, the representation of this matrices are those that we want to self-test. With equation 1 on the right hand side a1 c1, and using 1 we know that this is also psi, and a1 squared is identity, and c1 is the linear combination of b1 and b2. Okay, so we have this equation, and if we multiply a2 tensor c2 with equation 2, then we'll have this. Now this basically means that c1 square acting on the density matrix density on the Bob side should be equals to Bob side, and also for the c2 square. And if we have this density matrix has the full rank, so that that means basically that if we have some auxiliary degrees of freedom, then you can basically ignore those degrees of freedom. So for example, if let's say the entangled state is like this, so it's a state in the C4 cross C4. So it's a linear combination of 0, 0, 2, 2, and 3, 3. So there is no 1, 1. So this is, so we can always say that there is 1 degrees of freedom which is auxiliary. So this is actually acting on C3 equals 3C. So this is actually acting on 9-dimensional Hilbert space. We can just So thus, if the reduced density matrix has the full support, then rho inverse exists, and if we rho B inverse exists, and if we multiply on both sides, then I will get this two equation. And let us take this equation, and if we just replace C1 by B1 plus B2 by root 2, then we will get this one, and these are identities. So the anti-commutator should be 0, which means that B1, B2 should be equals to B2, B1. And if you multiply B1 from the left-hand side in both sides like this and this, then so this is B1 square, which is identity, and you will get this. And if you take the trace on the both hand side, then the B2 square trace of B2 should be equals to this, and since trace is cyclic, you can go you can move B1 to on the other side, and B1 is identity, so it should be equals to the minus of trace of B2. So similarly, you can show the trace of B1 is also 0. So what that means is, so B1. So let's say B1 is a Hermitian matrix that has +1 and -1 eigenvalue. So there exists a unitary that would make this B1 to be diagonal, right? And since the trace is 0, the only possibility is the number of +1s should be equal to the number of -1. Okay, so I don't know the dimension of the B1, but since the trace of B1 is 0, I know that indeed this should be the case. And by applying another, so there should be, so in the diagonal there would be equal number of 1s and equal number of -1, and then we can apply another unitary such that the eigenvalues are properly arranged. So in the first like box, all the eigenvalues are 1. Like in the diagonal matrix, the eigenvalue is 1. In this box, this should be a diagonal matrix with minus identity. It's just the interchange of the basis, and this is nothing but sigma z with the tensor product with some identity of B. Okay, this is this matrix. So we have the first measurement that there exists a unitary on both sides that makes B1 to be sigma z with identity. Now let me see so it's almost, I have 10 minutes. I will be a little bit faster. So if you take the general matrix B2, so the trace of B2 is also 0. So I know that B2, the dimension of B2 should be an even number. So this HB should be something like C2 cross H of B dash. Okay, so you can represent any arbitrary matrix in this way. So where like F00, F01, F10, and F11 are square matrices. Okay. Now, so and we know that B1 is Z tensor identity, so which is basically in this form. So this identity basically belongs to this, and the dimension of HB dash could be arbitrary. Well, so now we derive this formula before from the maximum violation this way, this formula. And I know now the B1 is this, and B2 is in general this. So if you plug B1 and B2, then you will get such equation, first matrix multiplication, and you will see this equation can satisfy only if this F00 and F11 is 0. So B2 would be a matrix something like this. Now, B2 is also Hermitian matrix. That would imply that F01 and F10 should be related by the by the dagger, and B square should be identity, which basically gives you this expression that F00 and F10 should be identity, the multiplication of these two matrices. And we can replace F10 by F01 dagger, so it would be like this. So B1, so let us now represent F01 by a matrix F, and I know that B2 would be something like this, F and F dagger, because yeah. Now there exists a unitary that keeps B1 to be the same, like Z tensor identity. The unitary is in this form. So for any, so I know that the B2 is in this form, and I choose the unitary to be like this. So you can check that this is a unitary, because F should be a unitary as well, because this should satisfy this. We have this equation, and you can check that this unitary makes B2 to be in this form, so which is basically sigma x times the identity. So now basically, so it basically shows that there exists a unitary that makes B1 to be Z and B2 to be X. And since the Bell inequality is symmetric with respect to Alice and Bob, I can make the whole calculation by taking C1 to be A1 plus A2 by root 2 and C2 to be A1 minus A2 by root 2. And we can do the calculation. We will conclude that there exists a local unitary on Alice's side that makes Alice's observable to be sigma Z and sigma X. Now, Bob's observable, we have checked that these are Z and X. Then we can apply another unitary on Bob's side, which is U tensor identity. U is basically some rotation. So this is X and Z, some rotation about Y axis. So these are the two. This is sigma Z and sigma X. So I will apply another unitary such that this comes to here and this comes to here. I can always do that. So such that B1 would be this and B2 would be this. Yeah, so this I'm doing for because the calculation will be simpler. So such that C1 is B1 plus B2 by root 2. So that would be Z and X. C1 and C2 would be Z and X, because this plus this by root 2 would be Z and this minus this by root 2 would be X. Now we have these two equations in the beginning, that is these two equations. That's A1 tensor C1 psi should be psi, and A2 tensor C2 psi should be psi. And now I know that A1 and A2 are X and Z, and C1 and C2 are X and Z as well. So this is the general state you can take, which acts on C2 tensor C2. So this is let's say this is A and B, and this is H A dash and H B dash. So this matrix is this vector belongs to A dash and B dash, and any general matrix that belongs to this whole Hilbert space can be written in this way, like in this way. This is not normalized, but you can normalize it later. But I have now two equations with A1 tensor C1 psi should be psi. So now I know that A1 and C1, so there exists local unitary such that it makes Z and Z times some identity. And Z basically flips the bit, Z basically keeps 0 and puts a minus sign if it is 1. And if you calculate this, then on the left hand side you will get this. And on the right hand side, it is the psi, the general form of psi. And if this equation holds, then psi 0, 1 and psi 1, 0 should be 0. So the psi should be in this form, right? And then you take the other equation, A2 tensor C2 psi should be psi, and A2 and C2 are X and X with some identity. So X basically flips the bit. So on the left-hand side, these two will be basically flipped. If you do the calculation, it's very easy. And if this this equation is satisfied, then F psi 0, 0 should be equal to psi 1, 1. So psi should be something like this. So now you can normalize it. So this is the maximally entangled state of 2 qubit, and this is some auxiliary state. So so this is the proof of the self-testing statement that if you violate this inequality maximally, then whatever be the state and the measurements, there exists to local unitary that brings the state to be maximally entangled 2 qubit state, and the measurements are the qubit measurements on the XY plane. So I think that's all I wanted to say. So if you have any questions, please ask.
Questions?
There is one question in the chat box.
Okay.
Saurav asks, can you please elaborate the part of security based on laws of nature once again?
Okay, well, so so the thing is, so in the classical devices that we have, the security is based on the fact that there are certain problems. Those are very hard to execute in classical computers. Okay, but there is no proof that in future whether there will be a quantum algorithm that could solve that problem efficiently. There is no proof of such thing. So in future, there is a possibility that there will somebody will propose a quantum algorithm that would solve that problem very efficiently, and thus the security will break. While if we have a quantum device, and if the device provides the device-independent certifications, what does mean is I have a set of device like this, and from the statistics, I can ensure that this prepares a maximally entangled states, and this is these incompatible measurements that are acting on the maximally entangled states. Then I am sure that whatever is in this device, the outcomes should be random. Okay, because there is only one way to reproduce the statistics. There is no other way, and the only way is to use the maximally entangled states and to use these measurements. So so this gives so this is not a proof of security, but intuitively it does not rely on anything else. It only relies on the observed statistics. So that's why the security is unconditional here. So there is the security does not depend on some assumption of the device or some assumption that this problem is difficult to solve or computational complexity or anything else. This security is foolproof security. Yeah, so this basically, if quantum mechanics is true, this is secure. So I mean, this comes from the laws of nature. That is why we are saying that this comes from the laws of nature. Okay, anything else? So another way to look at it is classical system could be, so if you have a complicated system, it would be difficult to describe the system. But in principle, according to the laws of nature, if I know the initial, the state and the initial position of and the momentum of the system, and the force acting on those systems, then I can predict everything. So, and you can also copy that system. So that the classical laws does not forbid us to copy the system, copy the classical system, or it does not allow forbid us to predict the outcome. But quantum system, there is an inherent randomness in it, and there are inherent property that systems cannot be copied, like the no cloning theorem and the related things. So that's why the security comes from the laws of nature itself. So it doesn't, yeah. Anything else?
Yeah, any other questions? See, Debashis.
Yeah.
This is your new work, right? Is it there in archive?
Yeah, it's in archive.
Very, very nice, very nice. In fact, I will myself work it out. We'll actually, leave it for the students, your, this handwritten notes and observables and operators. I actually will myself work it out. It's very nice, actually, very clean. In principle, it can be experimental its own, no?
Yeah.
I mean, I guess Professor Home must be, bringing it to the notice of some experimental people. Has somebody tested it?
You mean with experiment or without experiment?
I'm just telling you without, not very loudly, IBM quantum experience. I think this can be tested in IBM quantum experience.
Yeah, one can test there for sure, and I don't know whether somebody has done it or not.
I don't think so, because your paper is only last month, right?
No, it's a little bit old paper. So actually our paper is, so this is, you can certify a 2 outcome measurement and 2 qubit entangled state. But we have shown that it's possible to self-test D outcome measurement for any arbitrarily large D, as long as it is finite. And it's possible to self-test like the maximally entangled state of local dimension D. And yeah, so if you consider now D is equal to 2, then it boils down to the proof that I showed you.
Yeah, I think this is 2000, this is the PRA paper, right? 2017.
No, so this I will tell you I will send you the archive number of this paper.
You said it will put in our collection of we have this academic resource, and the ones you worked out in your hand, that is also part of that paper, huh?
Yes.
Okay, very nice, very nice. I'll work it out myself. Thanks. Huh?
Yeah.
So if there are no more questions, let us thank Debashis. Very beautiful talk. And things that I like about Debashis, which he has kept intact, is working out things by own hand explicitly. Very nice. Thank you, Debashis.
Yeah, thank you. Yeah.
So we will go to the last talk. I hope Professor Chaudhary has joined. Vinayak Chaudhary from IIST.
Namaste, Professor Panigrahi.
Oh, namaste. So very nice that you are here. So I'll very briefly introduce you. This is Professor Chaudhary is in IIST, erstwhile, this is Bengal Engineering College, Shivpur, and he was the mathematics head. He is the Department of Mathematics. He is from the applied math side and has very strong interest in varieties of things, like for example, gravitation, now quantum information, quantum computation. You see, coming from the mathematics background, he asked questions in very different ways, very rigorous. And I have read a lot of his papers on this communication, like, bidirectional communication, and how to use operators efficiently, how to choose, entangled states so that ifs cannot drop in. Very significant amount of works. So I request Professor Chaudhary to deliver his talk.
Thank you very much. So I will begin my talk by extending my heartiest thanks to the organizers, especially to our friend Professor Panigrahi for this invitation. So let me share this screen. I think the screen is visible now.
Yes, visible, yeah.
Okay. Let me test just one. So, let me begin. Actually, human being is characterized by technology. Wherever there was human society, there was some form or other of technology. And if you look into the development of technology across the ages, then there are many stages. But till the end of 19th century or early 20th century, it can be clubbed into one stage that essentially the technology was mechanical technology. That is, people just build houses and then fired cannonballs performed war with bows and arrows, and etc., etc. But after that, we came up with the electrical or electromagnetic technology, and its power is so much that it has taken us to the surface of the moon, and it is not very far off when it will take us to the surface of Mars. Actually, we are living in an era of electromagnetic technology. But at the same time, about 100 years back, there was a revolution in physics. Technology changed with the advent of science. But it is about 100 years that we first confronted the atomic and subatomic world and came up with a very separate type of physics and separate type of approach. This is, every one of us know that this is quantum physics. And with this quantum physics, we explained many things, but its extensive use is yet to be. Now we are in a position where we are going to launch technologies which are based partially or fully on quantum technologies. And it is believed that this technology will revolutionize our technological positions, and it is a futuristic technology. So what we are going to discuss here today is quantum communications, the fundamentals of quantum communications. I have been told that of the heterogeneity of the participants, and especially there are many student participants. And for that purpose, this lecture is semi-pedagogical. Although I will definitely touch upon some important points on quantum communication as we proceed. So essentially, we have as we told, that in the mechanical era of technology, we have the mechanical communication. Still it is there. That is the ordinary post, for example, then electromagnetic communication, which is the ruling technology of today. This is internet, telephone, and etc., etc. Now we are switching over to what is called quantum communication. Just like other quantum technologies, it is a futuristic developing technology.
Can you please make it full screen?
Full screen. I'm not well versed with the with this Zoom platform. Full screen. Where can I have that?
Sir, you can go to the view option.
Go to view option, okay?
Yeah, full screen mode.
Full screen mode, yes. That will make it full screen, okay? But in the full screen, how can I go down and up? Oh, this is the way we can go down and up, yes. So, now, what is to be in communication? The first question is, what is to be communicated? The answer is information. Now, what is information? Actually, information is something which the common layman understands, the scientists or the people associated with technology understand it in a technical manner. It is a very strong and very well-defined technical meaning. Now, this was given actually by Claude Shannon in 1948. This was a paper which is entitled A Mathematical Theory of Communications. It was in 1948 where he introduced the idea of information entropy and the idea of bit. Although Shannon refers to, accredits Taki with the idea of bit. Anyway, information is related to uncertainty. Where there is certainty, there is no information. Like this, idea is like this, that when I throw a coin, suppose, when we throw a coin, then if it is a biased coin, then for certain I know that there will be head appearing. So if I look at the coin and see the head, I have additional information. But if the coin is unbiased, or at least I know that there is a 60% possibility of a head or a tail or like that, and then I look into the result, or before I look into the result, whatever it may be, there is an element of information in it. So it is related to uncertainty. So anyway, I'm not going in to discuss the nature of information and how it is measured or like that. And actually, Shannon used a logarithm of base 2, which gave him, or rather gave us, I should say, the unit of information as bit, as binary digit. And for the purpose of using it in our machines, we require just a two-stage system or a binary system. An on-off switch is sufficient for that. And then we can store the information, we can encode the information, and etc. Whatever we want to do, we can do it, and whatever is permissible, we can do it, because there are many information bounds if we go into the mathematical theory of information and communication. So anyway, let us enter into the discussion on quantum information. Now, before that, let me state that the structure of classical information is through Boolean algebra. What is a Boolean algebra? Boolean algebra is a very vast thing, but anyway, for the purpose of storing and coding and etc. of information, we require just 0-1 Boolean algebra with addition, multiplication, and complementation defined in this. But in quantum information, this system is different. Suppose we are having two energy states of an atom, E1 and E2. It's well known. And then the system can be in a state of superposition. The KT is equal to alpha E1 plus beta E2. But if we look at the state E, we cannot have a direct access. It just goes to state E1 and gives me the result E1. I can have the result E1 with probability alpha square and result E2 with probability beta square. This information has, I should say, its storage, whatever be it, and its nature is richer than the classical information in the sense that we can have two states E1 and E2 for sure, but we can think of making linear combinations of them, and the possibilities of linear combinations are infinite. That is, with the preservance of that is assuring the preservance of probability, you can mod alpha square mod plus mod beta square equal to 1. You can have alpha E1 plus beta E2 with alpha beta any two complex numbers. And thus, it is apparent that when we are going to use qubits as our basic units of information, then it is definitely more versatile, but at the same time, it is probabilistic. That is a negative virtue for that, which we will come across. So unit of quantum information is qubit. Now, the stage is changed. You cannot simply have a Boolean algebra, because Boolean algebra will not allow you to have superpositions. That is linear combinations. But in quantum, or in the case of qubit, you can have. So you have, instead of E1, E2, which is a particular realization through two energy states of an atom, we just use 0 and 1. And with that, a qubit is written as alpha 0 plus beta 1. It is a member of the two-dimensional linear space, especially a Hilbert space. Now, what type of mathematics we require? Qubit is a member of linear space. So we require functional analysis for that. So mathematics is very, very different from the mathematics with which we approach the classical information. More specifically, we require the mathematics of Hilbert space. Why Hilbert space? Because in processing the information or doing other jobs associated with information theory, if we want to take it in the domain of quantum information, then geometry is very much required. In linear space, you don't have much geometry. If you extend the linear space to the case of non-linear space, then you can give rather you can give a meaning to length of a vector. That is, norm is nothing but a length. And if it is a Banach space, that is a non-linear space with completeness. What is completeness? It is mathematically a very great thing that every Cauchy sequence converges. It is the mathematical definition of that. And physically, it is the assurance of convergence and the assurance of existence of many results, which we will require in our sequence. And more so, it is not enough, because Banach space geometry is handicapped by the fact that there is no provision for understanding the angle between two vectors. This will require a further extension of this concept, and this is the Hilbert space, where you have the inner product which can be viewed in three-dimensional analogy. I say in three-dimensional analogy. The analogy may be a little bit far-fetched. Still, it is a guiding principle or guiding mechanism to our mathematics and to our intuition. And in Hilbert space, you have that developed geometrical structure, a robust geometry you have in Hilbert space, and you require that. And what are the operators you need? Yes, you need Hermitian operators. That is the dynamical variables, and two very important operators: unitary operator, evolution in time, as you use in ordinary quantum mechanics. Essentially, you are doing some quantum physics here, and projection operator, which is for the purpose of measurement. And we must be aware of the fact that not all types of mathematics which are available for dealing with the quantum world, for example, in quantum field theory, this is not really applicable just at this point of development of quantum information theory. There are very specific requirements of mathematics. Now, what is the definition, or rather, what is the role of information theory? Information theory is essentially concerned with representing data, that is source coding, then transmitting, and then storing. There are many certain source coding theorems and source channel coding theorems, etc., etc. So essentially, we will be interested, because we are going into the fundamentals of quantum communication, we will be interested in the transmitting part of the information. Now, for the purpose of transmitting quantum information, we require a quantum resource, which is called quantum entanglement. This is a primary resource for all quantum jobs, not to speak of, rather I should say for most of the quantum jobs, not to speak of only the communication system. Now, for our purpose, we will concentrate on the communication system and see how the entanglement can work or works. Now, before going into the detail of entanglement, let me show you just one thing, that what is entanglement? Entanglement, there is no entanglement with a single system. Two systems are a composite system, are said to be entangled. When they cannot be separated. Ordinarily, when they cannot be separated. What do you mean by that? In the Hilbert space, as you know, that a quantum system is generally represented by a vector in the Hilbert space. and the another system is represented by an element of another Hilbert space. If you want to just make a composite quantum system, then its representation will be through a tensor product of the Hilbert space. Now, it is not always possible to express any vector in that tensor product as the tensor product of individual vectors collected from the two spaces separately. And so you cannot, physically this means that you cannot separate them out ordinarily. You can definitely separate them out, but it will require special efforts for you. Ordinarily and automatically they will not be separated. This is the quantum correlation between them, and it has no classical counterpart. I will give you more details. Before that, we come to a little bit of historical note, because it will not only it is interesting by its own right, but also will shed some light on the problem of communication. That is, now it is known, and it's a part of general knowledge even, that the idea of entanglement was given in the paper of Einstein, Podolsky, Rosen, the famous EPR paper in 1935. And its use began to be explored not before 5 decades. Then what we were doing across this length of time, which is more than half a century. So this is interesting, because immediately after the publication of this result, of which entanglement is an integral part, and actually the argument of EPR is based on entanglement, there began a, I should say, intellectual debate. The Einstein versus Bohr-Heisenberg exchange. Possibly it is the most interesting intellectual debate of modern times. And for next about 3 decades, that is 30 years, the debate and the efforts were diverted towards the understanding of physics, towards philosophy, and etc. And this consumed a lot of efforts. Our main focus went there, whether it is possible to have some non-local correlations. This idea is very important, and we will see that this is something non-local which is central to the quantum communication. What do you mean by non-local is that if you want to just make an effort at this place, you will have to make it locally, in the sense that in the surface of the moon is just 1.5 light seconds away. If you perform something here and want to just influence something on the surface of the moon, you cannot do it before 1.5 seconds, because you will have to exceed the speed of light. But with the prior history, the 2 particles separated in different directions and are light years apart. Then the quantum correlation, which is non-local, implies in one sense I should say, because there were countering of these ideas, that this effect can be made known, can be made instantaneously, but from the information point of view, may not be known. Anyway, the debate went on until in 1964, Bell proposed an inequality which is known as Bell's inequality, a very powerful result in the history of physics, not only in the history of physics, in the history of natural philosophy, natural science, and in general in the history of understanding of nature by Homo sapiens. So it was a testable inequality. It has various forms. One of them is CHSH inequality, and there are some other inequalities. And this gave us an opportunity to test whether non-locality is possible or not. It is a experimentally testable inequality, but performing such experiments is not a very easy task. And also, regarding non-locality, different communication, different ideas came up, ideas changed, viewpoints changed. Anyway, the relevance of that and research on that is not yet finished. And we have different interpretations of quantum mechanics, and even today it is going on, and newer interpretations are coming up. Anyway, so this was in which our interest and our focus was diverted in this direction, and best brains of physics were engaged in that period to explore this domain. But in 1993, after, as I told, that after more than half a century, a paper was published by Bennett et al. This is actually the paper where teleportation, the name was coined by the authors. Teleportation was proposed, and it is through EPR channel and dual classical channel. As I told, that quantum technology is not something that we are bidding goodbye to the electromagnetic or mechanical forms of technology. It's not that. As it stands today, at least in quantum communication, it is with the assistance of classical communication that we can use the quantum resources. So this is the teleportation protocol, which was proposed in 1993. For that purpose, I will get back to a little bit of mathematics. That is, suppose it's something concrete one. You have a qubit like this one, A is 0 plus B1 in the Hilbert space basis 0, 1. Because why I call it a Hilbert space, I have just explained that because I will have the requirement of geometry when we go to more and more complex situations. And then for 2 qubits, if you have 2 qubits at hand, then it is represented in the tensor product of 2 Hilbert spaces, and the general form of that qubit is equal to this one, A00, B01, C10, and D11. A, B, C, D makes are so chosen. You can choose it in some other way, but it is convenient to make a choice so that alpha is normalized. That is as unit length. You take a bracket, bra vector, and a gate vector, you get 1. And this is the first one is the in the first system, that is in H1, from H1 system, 0 appears here. From H2 system, 0 appears here. For this, this is the general description of the 2 qubit. Now, you can use, now one thing is important by telling that the general description, what I mean is that all the qubits can be generated by linear combinations of just 4 vectors, 0, 0, 0, 1, 1, 0, and 1, 1. But you can change the basis. What is the change of the basis? Yes, you can do that. You can have an alternative basis, very famous, which is called the Bell basis. Yes, explicitly I have written, these are 4 because the Hilbert space basis has a fixed number of elements. So these are the 4 basis elements. Now you know these are called the Bell sticks. What are the bells? Any vector can be written again just as a linear combination of these 4 vectors. It can be done. So what is the importance of that? Take just first one, 5 plus 0, 0 plus 1, 1. And you will see that it is not possible to write them in the form psi 1, 0, 0, tensor product of psi 2, 0, 0. This is an entangled state. Entangled 2-particle state, or I said 2-qubit state. Qubits are sometimes realized 2 particles. Anyway, it's not of much concern, because when we are generally describing the procedure, then qubit is of our present interest, and this is an entangled state. You cannot simply write it in this form, and it is the simplest entangled state, but the most important entangled state, I would say. Now, entanglement maybe is, you need not think that entanglement is only, you can add another one, H1 cross tensor product of H2 and then another H3. You can add, and at the same time you can have an entanglement. This is another entanglement of 3 qubits. 0, 0, 0, 1, 1, 1. It has extensive use in communication problems and also other problems as well. And this is called, it is a very formal name, which is called G8Z state. It was first used by Galinger and etc. to other scientists, and so the name is derived from their name. This is called G8Z state. So one thing is important, that the concept of entanglement is not necessarily a bipartite one, it can be a multipartite one. So you have 3 qubits here, you can have n qubits, does not matter. Now I will describe the quantum teleportation protocol. So, what is quantum teleportation? Quantum teleportation is just transferring from one person to another person a particular qubit, which is arbitrary. That is, if I am given a qubit at hand, someone gives me, I will not look into the qubit. This is arbitrary. But I will put into the communication system that qubit, and it will appear in some other place, in some other person's hand, other intended person's hand. For that purpose, customarily, there are 2 persons. One is Alice and the other is Bob. Alice has the qubit. So the requirement is that a qubit to be teleported. So transmission here is called teleportation. It is to be teleported, a very special name when we use the quantum means of transmission of information, of qubits definitely. And there is, as I told you, and if you look back into the EPR paper, this is telecommunicating of an unknown quantum state. As I told you, unknown means it's an arbitrary, someone gives you and you need not bother what it is there. Just like a postman who receives a letter, when you give it to him in order to be delivered to some other place. Just like this, an unknown quantum state via dual classical and EPR channel. So a classical channel is there. That means supposedly a telephonic channel. It's a support of the whole system, as I will see. Then entangled EPR pair. As you know that the Bell states are actually referred to as EPR pair. There are 4 Bell states. These are the 4 Bell states, any one of them. The other name of it is EPR pair. Then performing a Bell measurement on the EPR pair. What do you mean by Bell measurement? That is, in quantum mechanics, we make a measurement. If we are doing Hilbert space quantum mechanics, we make a measurement with respect to certain bases. And after the measurement, the state is thrown into one of the basis elements. This is, we use Bell measurement. That means we use Bell states as our basis. Then manipulating the quantum state to one of the parties by unitary operation. As I told you, unitary operation, measurement, that is projection, these are required mathematical operations for the purpose of quantum communication. Then let us discuss this one. So this is our arbitrary qubit. This is in Alice's hand. And she wants to transmit it, that is to teleport it to Bob. And Alice and Bob, A means Alice and B means Bob, they are connected by any one of the 4 Bell states. What do you mean by connected? That this is the description of the Bell state. Take the first one. Does not matter if you take the second one, but let us take the first one for definiteness. You will see that the first qubit is with Alice, the second qubit is with Bob. And in this way, they are connected by the entangled Bell state. This is the quantum resource and quantum connection. Then what happens? Then we can see that this is the qubit at hand. And this is, the first one is the channel. And then the composite system. What is the composite system? It is that the channel is here and the qubit in the hands of Alice is here. With Alice, we use small a for the qubit and capital A for the qubit involved in the channel. Fine. So let us just rearrange and write it. Yes, we have written, rearranged and written that. Now, if you look into it, it is in a state which is with respect to the 4 Bell states. Phi plus, phi minus, psi plus, and psi minus. Yes, these are the 4 Bell states. But just rearranged it. Nothing. A little bit of algebra was involved in the whole exercise. Very little bit of algebra. Then Alice, what she does is that it makes a local measurement. It's not difficult because these 2 qubits are in the hands of Alice. So Alice can measure in the Bell state. And when she measures, she will be thrown in one of the 4 Bell states. This is the post-measurement scenario. After the measurement. So along with, if the Alice gets the second result, phi minus. So the whole system will be, with the tensor product will be thrown in that state. That is, the system will be thrown in this state. This is into tensor product of this one. This is by the law of measurement. And you don't know beforehand where you will be thrown. You just know that looking at it, you will just know that it is equal probability that you can be thrown in any one of them. So you are thrown. But beforehand, you don't know where you will go. This is the arbitrariness in the measurement procedure. Measurement procedure sometimes is viewed as something out of track from the mainstream of quantum mechanics. Why I will come to a discussion, and it has important implications on the measurement on the communication problems. And after the measurement, you were thrown in one of the 4 steps. Suppose you were thrown in the first, this one. Then what Alice will do, she will take the help of the classical communication channel, inform Bob that I have obtained this one. And Bob will definitely learn that I have obtained this state. And if psi plus is there, Bob will see that he is left with this state. But it requires some manipulation on the part of the Bob. The protocol states that when Bob is informed by Alice over classical channel that Alice is with this state of in her measurement, then Bob will do nothing. Do nothing means this is identity operator. But with phi minus, Bob will apply sigma z. With phi plus, Bob will apply sigma x, and with phi minus, Bob will apply sigma x, sigma z. And if these are applied to the 4 states respectively, then this is with I, and you can recognize that this was the original state which was in the possession of Alice, and sigma z is applied to it. You can readily see that the state is transformed into the original Alice state. And with sigma x, this one is transformed, and sigma z, if we apply it to it, it is transformed into the original state, which Alice had. Now it is in the possession of the Bob, and this is the end of the protocol. So in the whole process, you must know this correlation. So Alice and Bob must sit together and decide upon it, that if I receive this message from you over classical channel, I will use this one. And this is the total protocol. Protocol means this is prior arrangement. After the arrangement is completed, then whatever Alice had in her hand, it goes to in the hands of Bob. That is the end of the protocol. And by this whole process, you have been able to transfer the original qubit, which was in the hands of Alice. Now the point is, there are certain points to be noted. This is an amazing simplicity of the introducing protocol, and it is the first quantum communication protocol. And although at later times more complicated protocols were advanced, but all the protocols use the basic idea of the original teleportation paper. Now I will have a closer look at the whole process. Firstly, the first thing is that before that, let me tell you that we are using these states which are called max. Let me go a little back. Yes, 4 states, and I have written them as maximally entangled states. What do you mean by maximally entangled? You mean by maximally entangled something which has maximum entanglement. Is it that there is a variation of entanglement? Surely there is. And in the same line as the entropy which was proposed by Shannon, which gives a measure of information, arguing or rather borrowing the idea from there, we have measures of entanglement. You can see that the coefficients are equally distributed. That means its implication is that if you measure, then you will have this result or this result with equal probability. So with equal probability, if you have, then we say it maximally entangled. So it gives you a clue that it is possible that the entropy function, like summation pi log pi or like that, will give you a measure of entanglement. Yes, it is possible. And there are not only this one, there are negativity and etc. There are several measures of entanglement. One of them is this. And in that sense, or in that vein, we tell them as maximally entangled states. First thing is that, to be noted, is that we have ignored noise in this protocol, and it was not very imperative that in the introducing protocol paper there will be everything very complete. So the study of noise, that is environmental noise, which is very much present in every communication system. You cannot simply avoid the noise of the environment. So it has to be included in the whole protocol. And when it is included, then in the whole process, you will have to bring some other environment, that is tensor product with certain environment. And then the whole process will have its own dynamics. The environment may be changing with time. And this calls for the theory of open quantum systems. So what happens when the noise is considered? It becomes an open quantum system. And it has its own theories, and teleportation, to make practical sense, must be adapted to this particular system. And although I don't mention it, there are substantial advances in this direction. Not only this one, there are many types and many variants of teleportation. That I must say that I have also mentioned that whenever you go into the communication system, if you look into the texture of the whole mathematics or the texture of the whole engineering, then you will see that the basic idea of teleportation is definitely there. It is extended, molded, but still the fundamental is this one. That is, there is a channel, and then there is a supporting classical communication. Till today, we do not know how to communicate by using quantum laws without the help of classical channel. Another thing is what is difficulty. Rather, I should mention that before going into that, the practical implementation of teleportation. Yes, it's not a very far cry now. There were several experimental reportings of teleportation, but most encouraging is that one which was reported in Nature only in 2020 June. This is the reference in which we see that 1120 kilometer long satellite-based quantum communication has been possible. Before that, there were also teleportation experimental realizations of teleportation, but that was in very controlled atmosphere, because one thing is that the entanglement resource is fragile. And for that purpose, we have multi-hop teleportation. That means that we make it through grids. We don't want to teleport from Alice to Bob very far away, but we make intermediate receivers and senders. This is one way of dealing with the problems. Anyway, what are the primarily you see that Alice's results are 4. How the teleportation, practical implementation of the teleportation becomes difficult is that Alice has 4 results. Now, these are 4 entangled Bell states, maximally entangled Bell states. It's not a very easy task to just discriminate between, to know that what is exactly the experimental result, in the sense that the state discrimination is not a very easy task. It will require additional measurements or additional qubits to be added in order to make sure that what result has been found by Alice. This is by itself a challenging job. So whenever we go for practical implementation of teleportation, we are faced with, the engineering is definitely faced with very, very difficult problems. Still, it has been possible. And another thing is that it uses measurement. Now, measurement problem is somewhat which is not very comfortable in the domain of quantum mechanics. Many people felt uncomfortable with it because one of the facts is that measurement appears to be ad hoc. Why? There is a group of operators, essentially a collection of that is projection operators, and then suddenly some of the projection operator acts and then gives you the result. Why? What is the underlying cause behind it, and etc., is not well understood. Measurement appears to be a little bit out of track, and for that purpose, we have the theory of quantum decoherence. That means, which is a theory which is developed in this way, that it primarily treats not an isolated system, but a system along with its environment. As you see that whenever we want to make a physical theory, we just think of an isolated system. Not only it is in quantum mechanics, but it is always there in physics. First, we want to isolate the system from the environment, give it a separate treatment, and in this way bring out the theory. Want to see what actually the truth is, what actual truth is there, and what is actually the theory which is applicable. But the program of quantum decoherence is quite different. It says that actually we should treat not the isolated system, but system along with its environment. And then the total dynamics will finally lead to certain events or certain implications through which we can have an explanation of the measurement. Anyway, it is not that to say that quantum decoherence solves everything, but this is an effort towards this direction. And with this, from this point of view, there are important questions which are answered or partially answered, or I should say safely that it has or is claimed to have contributed in a separate way to the mechanism and to the formalism of quantum teleportation, definitely, and also to other quantum quantum communication protocols. And another important thing is that the qubit original qubit in position is lost to Alice. She is no longer possessing. You look, this is the Alice's result. The qubit has vanished and it has appeared in the hands of Bob. It is lost. So you will tell me that yes, why is it is not that Alice is just keeping a copy of that qubit with her and then making it? If someone gives me and tells me that just communicate something by any means whatsoever, then I need not know that, because it is arbitrary, and without the knowledge of Alice, it can be put in the quantum machine. And so, but without knowing it, without looking into it, I can put it in the Xerox machine, keep a Xerox copy of that, and then do the rest of the job. And there is no question of losing information. This is not allowed. This is another thing. You can say that this is a serious as I told you, that quantum based communication and information has both its positive and negative virtues. This is one which is cannot be made very welcome in the domain of quantum information in one sense, and in the other sense, it is welcome because hackers will have very less chances. This is the quantum famous no cloning theorem. Quantum information cannot be cloned. Why? Because if you have an empty qubit, how the copying takes place. You take one side, this is your qubit, and take an empty qubit E like anything, and then you apply a unitary operator on it, and you will have psi. That is, it is copied or cloned. Yes, if it is A0 plus B1, then if there is such an operator, we call it a machine. And really, when this operator can be engineered in some way or other, we call it, it becomes a quantum machine, quantum copying machine. And then psi, what does it look? If you just expand it and write it in this way, and then again, have another look. It is just a linear operator. Quantum mechanics is a linear theory. So you can write it in this way, and you have this one. Individually, it acts on this one 0. So 0, 0, and 1, 1. Now look at this expression, A0, 0, B1, 1. And here you see that this same expression is this one. But it should be for every A and B. Unless A is equal to 0 or B is equal to 0, you cannot sustain them simultaneously. There is a contradiction. And therefore, the quantum cloner does not exist. So it is not possible, and this was just a result of 1982, quite back. And in this situation, it is not possible for Alice to retain her quantum information with her. I think that I am running out of time, actually. I think my time is over, actually. But I will stop after giving some glimpse of two protocols, that is remote state.
You can go on for some more time, because you have up to, which question answer up to 8. So you can go on, no problem.
I can go on for some time, yes. So I will go on for another 5 to 10 minutes, I think. So the remote state preparation. What is the remote state preparation? It is like quantum teleportation. Everything is same, but one thing is that in the quantum teleportation, the idea was to teleport an arbitrary state. Now you know this state. So Alice wants to create a state which is alpha 0 plus beta 1. We have taken the normalization condition in the lab of Bob. For that purpose, we use a 3-particle entangled state. My purpose of just drawing your attention to it is that how the multi-particle, although 3-particle is the smallest multi-particle state, can be utilized. So we have a 3-particle state like that. And this is 2 are shared by Alice, A1, A2, 1, 2 is shared by Alice, and the 3rd qubit is shared by Bob. And Alice now chooses 4 mutually orthogonal states. Now, this is important to see that with alpha and beta differing from 1 by root 2, there is no reason to think of alpha and beta to be 1 by root 2. Alice is measuring in this, in this basis in which none of them are maximally entangled in the sense that we have discussed. So it is not necessary that we always need to have maximally entangled state, and it is also not necessary in the whole communication theory that maximally entangled states will always give better results, not necessarily. There is something called, which is measured something sometimes by fidelity. Anyway, this is a separate thing, will take us too far. Then phi can be written as, phi means this state, which is the quantum resource, can be written as in this way. It is as per our convenience we have written. You can see that it is written in that basis, although all the basis elements are not used. Then Alice will measure. After performing the measurement, we have Alice can measure and get either Xi1 or Xi2. If Alice measures Xi1, then Bob is left with this state, and if Alice measures Xi2, Bob will left with this state, and then again there is a classical communication. Otherwise, Bob does not know which state he is having and what to do, which things to apply. Then after getting the classical communication, Bob will apply, either will not apply anything, it is there. If he is informed that Xi1 is the result of Alice and with Xi2 the result of Alice, Bob will apply sigma x, sigma y in order to retrieve the state which was intended for him. So this is the remote state preparation. Another thing is that it will be interesting. It is the joint remote state preparation. What is joint remote state preparation? That means it is remote state preparation, but 2 members jointly make them. Now, this is the state. And in this state, we write alpha is equal to x0 e to the power alpha 0, x1 e to the power alpha 1. This state is not known to Alice. And now Alice and Bob are the 2 senders, and Candy is the receiver. And now the point is that x0 and x1 is only known to Alice, but not alpha 0 and alpha 1. Had it been known to them, Alice should have the whole information available to her. No, she does not have. She has the partial information of the state, and Bob has the partial information. Alpha 0 and alpha 1 is known to her. What to do? Again, there will be a GHZ state. My point is to show how the multipartite entanglement can be used. After that, Alice measures in this state, in this basis. How she can form this basis? Because Alice knows what x0 and x1 are, and she can construct this basis, no problem. But she cannot go any far because alpha 0, alpha 1 are not known to her. And after that, the original state could be written in this form with Xi1 and Xi2, one of the results, then Alice, which Alice has, then Alice's outcome is Xi1, then the whole state is collapsed to this one. We accept the collapse of quantum mechanics, in the theory of collapse in quantum mechanics. Of quantum decoherence are like that. But I should say that quantum decoherence has very important implications in the quantum communication system you can have an idea of that, because quantum decoherence deals with the system and with the environment, along with the environment. That is, it jointly deals with the system and the environment. And in the whole process, the environmental noise is taken into account, which, if we treat some system as an isolated system, we cannot take that. So environmental noise, what type of noise it should be brought in, its stochasticity should be examined, and etc., many things will be there. But in the approach of quantum decoherence, it is possible to have an integrated treatment of the system and also of the noise. Anyway, we are not concentrating just for this here on that. Just for information, I have told. So if the Xi1 is Alice's outcome, then the state goes to this one, collapses. And if Xi2 is Alice's outcome, then it collapses to this state. Let us take Xi1. And then Bob chooses to a measurement in the measurement state, this one. This is possible for him. Why? Because alpha 0 and alpha 1, these are information related to the state which is available with Bob, but not with Alice. Now Bob knows that, and so he constructs these two states. After that, let us assume then Bob's outcome result may be eta 1 or eta 2. Yes. These eta 1 and eta 2 are Bob's basis elements. After the measurement, the state is either this one or this one. Accordingly, the Candy will apply either I, that is, will apply nothing, this is identity operator, and or sigma set, and will convert it to the original state which was intended to reach. But every state in every stage you must understand that without the support of classical communication, it is not possible. Quantum means, as the theory of communication stands today, the quantum communication alone cannot stand on the shoulder of quantum physics. It requires classical communication channels for its performance. So this is all about this one. And another thing is that I have given here in the last two protocols, you can see that 3-particle entangled states are there. But entanglement can be n-particle, and so the task can be extended, the task can be enhanced, task can be done. And now the point is that with the increase in the number of participants in the entanglement resource, we call it a resource, quantum resource, this is the technical name. The more and more complicated communication tasks can be worked out. But the problem is that to create multi-particle entanglement is not that easy, and technologically not yet that much viable. So this is all about what I have to say, but I must stop with one word, that what I have told here, it is a somewhat, I should say, in a semi-pedagogical manner, not really going into touching over the basic ideas, not really going into detailed technicalities, too much of technicalities. I have not presented something which involves too much of technicality, but really if you want to do something very worthy with the quantum communication and information system, then the mathematics, as I told you, that it is Hilbert space, mainly Hilbert space quantum mechanics, but it requires, as you know, the structure of the Hilbert space is very, very complicated. It really requires very complex mathematics to understand and to make an advancement in this whole domain, in this domain of quantum communications. And more so, only when we are talking of these protocols and etc., these are the possibilities which are allowable. Now it is up to the engineers to make them into realities. The applied mathematicians and the physicists can give the possibilities. And it is the experimental physicists and more so the engineers who should spell them out into machines and make them into realities. And it is a ray of hope that 11-20 kilometer long quantum communication is something very encouraging. And I will ask everyone to look into this particularly this, I don't know whether anyway, I'm not, yes, this one. Particularly this communication in nature has been a very great source of inspiration for me in particular. Stop here and thank you all.
Yeah, thank you, Professor Chaudhary. Very illuminating talk. Now open for questions and discussions. So the communication protocols you described, like bidirectionals and things like that, they will be very useful for distributed quantum computing also, right?
Yes, yes. Actually, these communication protocols, it will not be correct to think them as just sending the quantum information from one place to a very distant place. Not really. It is the only scope of that. It has very important implications in quantum communication as well.
Right.
I mean, quantum computation as well. I mean that. In quantum computation also, small-scale teleportation type realization through entanglement, it is very important.
And also remote state preparation. You want to, to remotely create something somewhere, in a distributed kind of architecture. It will be very useful.
It will be very useful, surely.
Now, in your case, for example, did you see any kind of states are more useful, like cluster state or GHZ state as compared to other states like W?
Just, I did not follow.
See, for example, from teleportation point of view, W states are not good, symmetric W states, whereas GHZ state is very good.
Yes, W states are also used. W states are also used. I have not mentioned here W states, and there are also other states. W states is also very useful, very useful.
Okay. So they may not be exactly useful for teleportation, but they will be useful for other kind of computational tasks. Yes.
Other types of it is not only confined to teleportation. Sure.
So anything from chat box?
So there is one question from Alok Kendu. Can you unmute yourself and ask the question, because the question seems not specific? So.
Hello, sir. First of all, thank you for this good session. And sir, my question is that in this method, I mean in quantum technology, is there any possibility of describe some specific information?
Is there any possibility of?
decrypt any information, I mean very secured information, if we want to send from one place to another?
Yes. So why we require quantum means of communicating? You have internet in your hand. You can communicate with the other part of the world in fractions of seconds. Still, why you want quantum means of communication? Because you know that internet safety is not very reliable. Whatever safety system you use, whatever antivirus or other types of things you use, it is not. You cannot finally rely on them, as our everyday experience teaches us. But in quantum, if you see the quantum public key distribution, quantum cryptography, and etc., you will see that quantum systems are more robust and more secure. And quantum security, if it can be actually materialized through machines, and it is hoped that it will be materialized in near future, it is hoped like that. Then it will definitely give you enhanced, much enhanced security, definitely.
Okay, sir. Thank you, sir.
There is another question by Saurav. Saurav, can you unmute yourself and ask the question?
Yes, so my question was that, like you mentioned, that teleportation of a photon can be done from one point to the other via some intermediate points, which will make the process more feasible. So if number of points are increased, then will there be a time lag, considering the case that when no intermediate points are there?
Yes, definitely. There will be a time lag, and this will pose not only time lag, not only just the loss of time, but it will also pose additional complications to the protocol, definitely. And these additional, if you look into, this is called multi-hop teleportation protocols. And in this process, you will definitely have, it is just like a relay. And you can look I believe it is in 2021, this year only. You can look for one paper which I see, but I cannot really quote exactly correctly, appearing in Physical Review A, in which you will find a detailed analysis of this particular type of communication. Just look into February or March issues of Physical Review A, I think, if I'm not that very much mistaken. You will find that these are actually identified, and how to rectify themselves. This is also a challenge, actually. Give additional complications, no doubt about it. Just in the electrical technology, you will see that relays are there, and there also you find advantages, and as well as boosting up of the voltage is there, but as well as there are complications.
Right, sir. Right, sir. That's why I was actually asking this question. Thank you, sir.
Sarang, any more questions from there?
No, there are no questions left in the chat box.
Okay, so in that case, thanks, Professor Chaudhary.
Okay, thank you very much.
And hope that near future we should meet in person.
Sure. Definitely.